So, so it's kind of almost midnight here. Okay, so I will try to tell you some aspects of work I did recently. Actually, well, this has been going on for several years with Bruno Balthazar, who just graduated and will be moving to Chicago, and Victor Rodriguez. Maybe I should begin by describing the kind of the broad motivation of the series of work, and why we are, started revisiting sequence-1 string theory, and what are the current kind of interesting questions that we're trying to explore. Now, what I view as the important physical motivation in retrospect is a little different from the original motivations. Originally, we started working on this several years ago because at the time, in some other unrelated work with Scott Collier and Min-Jae Cho, we obtained some nice method of computing efficiently numerical Virasoro blocks on puncture Riemann surface and higher genus, and we want to find some application of that method, and that allowed us to actually relatively efficiently numerically evaluate in an honest way sequence-1 string scattering amplitudes from the worldsheet perspective. But since then, the project kind of took on a different direction, well, in different directions, and that's what I'm going to tell you about. So first, let me describe our goals. So why sequence-1 string theory? Of course, as is well known, the sequence-1 string theory, which I'll kind of briefly recap for people, I guess maybe the younger people in the audience who are not as familiar with the story. There's duality between sequence-1 string from worldsheet description and matrix quantum mechanics. But in retrospect, now, sort of the slightly new aspect of this is that I'm going to promote this duality from what there was, I think, traditionally thought to be a perturbative duality to a non-perturbative duality. So on the worldsheet, I mean, the sequence-1 string theory is kind of, in my opinion, one of the nicest, perturbative string theories to study, because it is the only bosonic string theory that actually makes sense at the quantum perturbative level and has a space-time interpretation. I'd like to emphasize time. The usual critical string theory that one would like to talk about in textbooks, which lives in 26 dimensions, is not consistent at the quantum level, even at level perturbation theory, because of tachyon. And the problem is really fatal. The sequence-1 string theory is the only version of the bosonic string theory where we have a worldsheet formulation in terms of the conventional CFT coupled to BC Go system, and has a time in the target space. So the worldsheet theory, as well known, involves a time-like sphere boson together with the sequence 25 Liouville theory. These comprise the sequence 26 worldsheet matter sector of the worldsheet CFT. And there's a genus expansion as usual. The matrix model size, as I'll review shortly, at least within the sector of the matrix model that's due to the closing sector of the sequence-1 string theory, this matrix quantum mechanics is equivalent to a system of free non-relativistic fermions, where you have some, non-relativistic Hamiltonian for the fermion with the upside down in the harmonic potential, and the closed string vacuum corresponds to the Fermi sea that fills the right side of the potential, and the closing states themselves are collective excitations of the Fermi surface, which can be thought of as particle-hole pairs. Now, non-perturbatively, so usually in the textbook from worldsheet formulation of string theory, one says that, okay, so you can write down, vertex operators associated with asymptotic states of the string in Minkowskian space-time, and then there's a prescription for computing perturbative S-matrix elements. But that worldsheet prescription based on the genus expansion is a priori entirely perturbative. And of course, it's well known in string theory that there are all sorts of non-perturbative effects that are crucial for the consistent string theory. They are not always computable. Sometimes some of these non-perturbative effects are captured by the effect of D-instantons, which I'll spend some time discussing shortly. It's the understanding of how to exactly compute the D-instanton effects for closing amplitudes is incomplete. And part of the work I'm going to describe is to try to learn some lessons about the non-perturbative correction to closing amplitude in the context of sequence-1 string theory, where there's a matrix model you can compare with and check. Now, on the matrix model side, this conventional description, where you fill one side of the Fermi sea, obviously looks like it's only defined perturbatively, because non-perturbatively there's going to be tunneling, conventionally, in fact, if you look at papers in the early 90s, I think the kind of point of view that was taken was that, well, first of all, you have a duality that was believed to be true perturbatively, and non-perturbatively, one does not know a priori the complete definition of the string theory from the worldsheet perspective. Now, if you look at the matrix quantum mechanics, you can imagine many ways to complete this picture non-perturbatively, because after all, perturbative effects do not know about tunneling or what is on the left side of the Fermi sea. So you could imagine, fill both sides of the Fermi sea, or you simply put a hard wall, and remove the other side, so there's no tunneling. So these are various possibilities you can try to use to complete, quote unquote, the matrix quantum mechanics non-perturbatively, which would agree to all of perturbation theory as far as the perturbative scattering amplitudes of these closed string excitations are concerned. And the traditional point of view was that any of these can be viewed as a non-perturbative completion and would define the non-perturbative version of sequence-1 string theory. That is not going to be my claim in this talk. In fact, I will claim that there's a preferred non-perturbative completion.
Sorry, can I ask something?
Yes.
Could you say again what decides what if the wall is finite or like a infinite wall?
Sorry, you're talking about this picture here?
Yes.
Oh, I'm just giving you some random example. I mean, this wall will be like an infinite potential wall, yes. So this was in fact the example considered, for example, in the paper by Moore, Plesser, and Rangulen.
Okay.
It was called like a theory of type 1 or type 2 or something. So it sounds, you can do whatever you want. Okay, so you can on the left side, but I'm going to, but this is not going to be so relevant to what I'm going to say, because I'm going to claim that actually the natural rule that we usually follow for formulating D-instanton corrections with closing amplitudes will select one, and to my knowledge, only one natural completion of the matrix quantum mechanics, which is neither of these options. So this first one, of course, is known as the type 0b matrix quantum mechanics that has been conjectured in the early 2000s to be due to a different string theory of the 2D target space, namely the type 0b string theory, where with n=1 supersymmetry on the worldsheet and so forth. Now, a perturbative set of that will be identical to sequence-1 string theory, but non-perturbative, they are very different. So that's what I'm going to claim, and I'm going to come back to this. I'm going to comment on the difference between the type 0b matrix model and the non-perturbative completion of the C=1 matrix model, which I will describe shortly. Okay. Any further questions on this point? I mean, this is so far just some general motivational remark. I mean, I'll come to this in more detail.
Can I ask a question?
Yeah.
So in the two-sided story, I mean, there is quantum tunneling, which
Yes.
has been computed before. So you're saying that that's not to be. I mean, it exists. The effect does exist, and therefore
Yes.
there could be some interpretation of that in the string side of the story.
So my claim is that that tunneling effect you can calculate on both. You can calculate the matrix quantum mechanics, and the explicit disagrees with the D-instanton effect in C=1 string theory. And it shouldn't agree. There's no reason why it should agree in the first place, because that was supposed to be, at least if you believe the conjecture, supposed to be due to type 0B string theory, which has a totally different worldsheet description. The worldsheet theory is n=1, matter coupled to n=1 Liouville. And in that case, the structure D-instanton effects are also different. There are D-instantons and anti-D-instantons and so forth. And one has to worry about NS sector, R sector. So that's a totally different story. It just happens that the perturbative subsector of that agrees with C=1, but non-perturbative, they're just different.
I see.
Yeah, so that'll be the claim. But anyway, I'll come to this different sector, but most of this talk will just be on the C=1 story.
Mm-hmm. Thank you.
Yeah. Okay. All right. So let me comment on this trying to understand D-instanton effects. So I would like to try to understand the D-instanton effects in the first principle formulation. Now, I should say that I see that Ashok is in the audience. I mean, there was a nice series of lectures Ashok gave just not so long ago on a systematic approach to D-instanton effects based on open plus closed string field theory. What I'm going to discuss here is a low-tech version of that, which I will not worry about some of the subtleties of string field theory. I'll still try to stay as close to the on-shell formulation as possible. But we'll see that some of there'll be some subtleties that will require the open plus closed string field theory to fully resolve. So I should say that a string theorists will talk about D-instanton effects all the time, but most of the time we're almost never able to compute this from first principle. Because most of the time when we claim that there's some known D-instanton effects, we're basically cheating by constraining the answer by some constraints from supersymmetry and so forth. One of the original honest attempts to study D-instanton effects was work by Green and Gutpearl in '97, where they study some full graviton scattering in 2B theory, type 2B superstring theory in 10 dimensions. And they considered, in particular, the one instanton contribution to the full graviton scatter amplitude, but as viewed as a momentum extension, the first non-trivial correction to the supergravity amplitude, to do with supergravity amplitude, is R to the 4th term. So they went out the start of the computation, and basically the computation involves sort of the graviton vertex operators inserted on 4 disks. All these boundaries of disks on the same instanton. So this is actually a connected contribution to kinetic amplitude, even though the diagram looks disconnected. So this is the computation that they were trying to do. Now, one thing they were able to show is that it reproduces the correct structure of the R to the 4th term, but actually that's fixed by supersymmetry, fixed by space-time supersymmetry. So, and if you set the computation correctly, that this has to be the case. And really, then this one instant contribution to R to the 4th term boils down to the question of the overall coefficient. But Green and Gutpearl actually were not able to fix coefficient because they do not know the a priori normalization of the measure when you integrate over the moduli of the instanton, namely the position of the, the coordinates of the instanton. So actually, up to structure that's fixed by supersymmetry, they didn't really have anything to check. However, it is known, well, wasn't clear at the time, but in retrospect, it's clear that the coefficient of the R to the fourth term in the full Gaussian amplitude in type 2B string theory is actually completely fixed as a function of the coupling by S duality. If you compare the answer with S duality, then in some sense that fixes the normalization, which fixes the measure of the integration over the instanton moduli space. And this normalization can fix once for all. So in some sense, Green and Gasparo, their calculation really serves to fix the normalization of the integration of the D-instantons moduli space by comparing the answer with S duality, which is a property you would like to impose on what you think the type 2B string theory should obey. Okay, so I will do something similar in the C=1 string theory. I will study some effect of D-instantons and closed string amplitude. And once again, we don't have an a priori way to, within the worldsheet formulation to compute the normalization of the measure, but it'll be fixed once for all by comparison with the matrix model dual. I should contrast this with the situation in quantum field theory where you have a path integral formulation, because usually when you have a path integral formulation in quantum field theory, you think of the instanton as a settled point of the Euclidean path integral, and you can study the fluctuations around settled points and integrate out the fluctuations that allows you to compute actual, allows you to derive the normalization of the measure. We don't have that in string theory for the D-instantons. Because you cannot describe these instances as a settled point of some closed string field theory. That we know that cannot be the case. So there's no known prescription to the best of my knowledge. But if you follow our notes, it'll appear to be the case that modular of field authorities, including the normalization of the measure, we do have a more or less consistent prescription of capturing the D-instanton effects. And this over normalization can be fixed by some duality argument. So that's one subtlety that one would encounter. Another subtlety that we would encounter in commuted D-instanton effects, which Green and Gasparo would have encountered had they gone to the next order in the expansion in this string. So the leading order, you only have these disks with one closed string insertion. By going to the higher order, you will have encountered, for example, this with two closed string insertions. And actually, so this boundary is on the D-instanton boundary condition. Actually, I think if you have thought about this kind of this 2-point amplitude, when you interpret this as a 2-point amplitude of closed string scattering off the D brane, you know that there's a open string divergence. When the intermediate, if you cut this in this way, when the intermediate open string goes on shell. Now, of course, for closed string scattering off the D brane, you can we understand physically why there should be this open string pole. But for a generic momentum of the closed string, the open string momentum, which is along the direction of the D brane, will be off shell by adjusting the scattering angle. And so the amplitude will be finite. But if you have a D-instanton, this open string, the open string mode, there'll be some open string mode that if it's on shell, it's always on shell because the D-instanton has no, world volume direction. So there'll be a divergence through exchange of some on shell open string mode that you cannot remove. So this is always divergent. So this diagram makes no sense. It's always infinite. So what do you do? And this divergence is a divergence of logarithmic type. You would expect that has a physical meaning. And in fact, this was the mechanism for canceling this divergence was understood by Joe Koczynski back in '94, even before the D-branes were the role of D-branes were understood. So the point is that there are other diagrams of different topology that look like this. So let's say this project operator 1 and 2. Such that they also have their own analogous open string divergence from cutting this annulus. And this divergence is cancel against each other. So the divergence is cancel divergence. So this is kind of an open string, open close version of the Fischler-Susskind mechanism. So we call this the Fischler-Susskind-Kolchinsky mechanism. And this will be important for the computation I will describe later. Okay, and this is a very general story. This also applies to superstrings if you go to the order where this divergence is relevant. I should say that while Kolchinsky already understood that this divergence can be canceled by summing over these diagrams of different topology, what he did not explain is how do you fix the finite part, because these divergences are of the logarithmic type, and if you want to cut up the logs, you have to make sure you cut it consistently. So to get the finite part requires open plus closed string field theory, as Ashok explained to us recently. Okay, so now there's a third motivation for trying to, why the single-side string theory is a useful toy model to model of string theory to study, is that it provides a setup in which one can consider a stringy model of black holes. Now, I'm just going to sketch some kind of motivational, remark and some kind of speculative comments here. This is not in the papers that we've published so far, but it's some work in progress. By the way, I think this is a kind of a very long introduction, which I don't know, might end up being like most of the talk, but that's okay. It's been known for a long time, or it has been suggested for a long time, that this famous, cigar geometry, also known as the 2D black hole, is a background. Let's say this is a closing background. Background of C=1 string theory. That is, if you start from, well, I mean, this is supposed to be the case because, well, you think of this as the Euclidean time direction, and think this direction is similar to Liouville direction, and so heuristically, because the cigar asymptotically also has linear D-instantons, so heuristically one would like to think of this. I guess actually Mike mentioned Liouville. Here goes this way. Think of this as some kind of deformation of the C=1 string background, which is from Worldsheet point of view involves a time-like boson and the Liouville CFT. This led to a great confusion, and because if you this question of is this a state in the single-strand string theory or not? Can you create this by scattering closed strings? Whereas in the matrix model, there's a great deal of confusion. I think there's actually a very clear picture of where the black hole is and how you understand this in single-strand string theory, which was basically explained in an obscure section in a paper by Formal Decina in 2005. And I think this paper, Formal Decina on the long strings and single-strand string theory, has a lot of stuff. And there's one section that has this very nice suggestion, which I did not really appreciate until relatively recently. The basic point is that the black hole, you cannot find it within the closing sector of single-strand string theory in a sense. you have to extend the string theory to allow for FZT branes. So let's say put it this way. So there's a dual direction in space-time. There's a dual potential, like so. There are these FZT branes, which are semi-infinite. They extend from the all the way from the asymptotic weak coupling region to some finite distance, and there's some modulus that kind of controls the position of the tip of the FZT brane. You can put as many of them as you want, a priori, but because these FZT branes are in some sense, half space filling, and they extend all the way to infinity, and they're infinitely massive objects, they should be sort of changing the background of sequence-1 string theory. And if you add this FZT branes, so this FZT branes cannot be thought of as excitations within the closed string sector, and you will not find it in the matrix model. In order to find this FZT brane, you have to extend the matrix quantum mechanics. And now this is related to the black hole by taking some decoupling limits. So I think maybe I will not discuss this in detail right at the moment, because otherwise I will not get into the content I do want to explain in more detail.
But quick question, G.
Yeah.
Is equivalent to just moving away from the singlet sector of the quantum mechanics?
No, not quite. Almost. Well, it's closely related. Maybe let me elaborate on this point a little bit. So, in fact, before talking about connection to the black holes. So, how do I understand this FZT branes? Well, there was a vague proposal made by Davide Ghiotto, which suggested that adding FZT brane requires coupling the matrix quantum mechanics to a fundamental fermion. I think his proposal is morally correct, even though details have not actually been fleshed out, which is actually very non-trivial. Now, there is a limit of this proposal that has been understood, which was understood by Huang's paper in 2005, and that's the long string limit. So the claim is that in the limit, so let me redraw this picture. So here's Liouville, and here's the Liouville potential schematically. In the limit, where you send this S parameter to infinity, so the FZT brane retreats all the way to the very weakly coupling region. So its effect on the closed strings, in the bulk is kind of negligible, okay? But you consider a very high energy open string, or several very high energy open string modes, living on the FZT brane. This open string, they are living on the FZT brane, they kind of shrink to a point. But if you have enough energy, once you move it toward the tip of the FZT brane, it wants to extend. The ends of open string are stuck on the brane, but the bulk of the open string can extend all the way into the bulk. Okay, so this is the so-called long string. So in the limit, where the FZT brane the FZT retreats off to infinity, but open string has enough energy to go into finite distance in the bulk. In this double scaling limit, one understands the precise view of this in the matrix quantum mechanics. So this long open string, the so-called long string, is due to a state in the matrix quantum mechanics in the non-singular sector, non-gauge singular sector, non-singular sector. So each long string corresponds to a adjoint representation. So you have 3 long strings. You'll take adjoint, tensor, adjoint, tensor, adjoint. So in such a representation of the matrix quantum mechanics, it's similar to kind of adding some classical Wilson line and some kind of classical quark source. You will be able to identify the precise scattering states that correspond to long strings as well as closed strings. So this picture, was proposed and conjectured in Huang's 2005 paper, and he gave some preliminary evidence for this. In our paper from a couple of years ago, we did a precise perturbative calculation involved the scattering of long string with another long string, or also as well as the scattering of a long string with a closed string, and we found some extremely striking match at the numerical level with a corresponding computation in the dual matrix quantum mechanics. Okay, so this is a theory which I can describe, but I'm afraid that within any reasonable amount of time, I have to choose between this and the topic of the D-instantons. Maybe I will. I was trying to say more about the D-instantons than this, but I could certainly get into say a little more about this later if there's time and space.
Thank you. Thank you.
Yeah.
Yes.
Sure. Okay. So okay. Now let me get to the actual details. So perhaps I should begin by describing the matrix quantum mechanics a little bit, because I want to explain what is the proposed non-perturbative completion of it, and what the structure, what is the kind of structure we want to recover from the worldsheet perspective. But before that, I should maybe, okay, I also want to kind of briefly review the status of perturbation theory, because historically there has been a great deal of confusion about, how does the duality really work even at the perturbative level, which I think we have more or less kind of understood, at least computationally, exactly what is going on. But let me first kind of recap the matrix model, and we'll discuss how this works at the perturbative and then the non-perturbative level. So the matrix quantum mechanics. So far, I'm just going to discuss a single sector. I'm not going to worry about the long strings or SDT brain and things like that. So this is the fully gauged matrix quantum mechanics. So we can write some X, which is n by n matrix. There's some potential. There's usual Hamiltonian, like so. And we're going to, as usual, this potential is the form minus x4 over 2. And plus some, if you want to regularize it to make it bounded from below, you can do that, but that will be not so relevant for what I'm about to say. So the wave functions are going to be functions of this n by n Hermitian matrix. But it's also going to be required to be UN invariant. This is what it means to be gauging in Hamiltonian language. If we, we can always write X as omega inverse lambda omega, where omega is a UN matrix, and this capital lambda is diagonal matrix. So if you do that, then we can express this wave function as as a change of variable as a function of lambda and omega. And to say that we're in a singular sector, this means that the omega dependence drops out. Now, this Hamiltonian just involves some differential operator on X, which can be re-expressed in terms of differential operator on lambda and differential operator on omega. This can be expressed in terms of UN rotation. So at the end of the day, you can rewrite the Hamiltonian in terms of differential operator acting on lambda and on omega, which is the UN rotation angle. And it turns out that it can be written in the following way. So let me write. So it turns out that we can write this Hamiltonian as delta inverse H prime delta, where delta is the Vandermonde, lambda I minus lambda J, I less than J, where these lambda I are eigenvalues of X, as above, where H prime takes some simple form. The point is that H prime is going to be effectively the Hamiltonian that acts on a different wave function, which is related to psi by the Vandermonde, by rescaling by the Vandermonde. So H prime is takes the following form. So sum over I. This is an old story, but just write this down to illustrate the logic, to remind people. Okay, so without imposing UN constraint, this is identity. So you can write the Hamiltonian in this way. Now, where this Rij are the UN rotation generators. If you take this H prime and act on a wave function that is independent of omega, that's UN invariant, then this term will drop out on singlet whereas this first term is the Hamiltonian of a system of free fermions, non-relatively free fermions. The reason they're fermions is because psi was completely symmetric in the eigenvalues, but the psi prime, which is the wave function that H prime acts on, differs by this factor of the Vandermonde, and it becomes antisymmetric for the eigenvalues, which is the position of each fermion. Now, I should emphasize that if you want to go to non-single sector, which, as I mentioned earlier, has to do with this long string that is, closely related to the FDD brain and ultimately black holes. Even I didn't actually explain what is connection to black holes. For that purpose, you have to study this non-single sector. And in the non-single sector, this last term will be important, and the fermions will actually be interacting. So this is actually a much more non-trivial and more interesting system. But for now, I'm going to forget about this term since I'm just going to restrict the singular sector. Okay, so now in the singular sector, at least perturbatively, the proposal is that we want to consider the state in which we fill one side of the potential of the the system of free fermions, and this corresponds to in the phase space, of course, P lambda and lambda. It corresponds to filling this right side of this hyperboloid. Now, a excitation of the kind of low energy excitation of this Fermi C are represented by particle hole pairs. So you kind of bring a fermion outside of the Fermi C. So you have this particle hole pair, which can be equivalently described as a ripple in the semiclassically of the Fermi surface. But the point is that this ripple of the Fermi surface, as it kind of moves along in the phase space, due to quantum effects, H-bar effects, they are actually effectively interacting even though the fermions are free, and one can actually compute exactly their S-matrix elements. This is the easiest to describe in terms of the particle hole prescription, which can be made precise also non-perturbatively, and that's the prescription I'm going to be using. So I'm going to follow the prescription of more Plesser and Ramgoolam. This goes all the way back in '91, where basically the picture is the following. So you have this these particle hole pairs, which are the closed strings, and you can think of each closed string is made of a fermion and a hole, and draw a diagram of scattering like so. So let's say here's the reflection of the particle, here's the reflection of the hole. These interaction points, they represent the reflection of this potential barrier. Now, a similar diagram can, for example, also describe the scattering of one closed string into two in this way, for example. So this represents a 1-to-2 scattering. This is 1-to-1 scattering. You see that in these two examples, actually, they both involve the particle hole amplitudes, but the energies are distributed a little differently. In some sense, this kind of scattering is kind of in some sense very trivial. So all that's happening is the fermion getting reflected, but the way that the particle number can change at level of this closed string modes or these particle hole pairs. One way to think about it is just that the particle hole pair you have like this can be interpreted as a particle hole, but another particle that fills this hole and another hole and a particle and another hole. So these two are the same hole and these are the same particles. So you can interpret this as three, for example, particle hole pairs. That's ultimately the reason why these particle hole pairs look like effectively they can scatter and create, the particle numbers can change. And there's a precise prescription for that. Now I should say that while in this prescription here, while this reflection amplitude of the particle is just the actual non-relative physical quantum mechanics reflection amplitude of the fermion, that's dictated by the Schrodinger equation for a single fermion. This reflection amplitude of the hole is a little bit tricky. This because the hole is not a particle. The hole is a the definition of hole requires first talking about the Fermi sea. So the precise definition of the hole depends on what the Fermi sea is, and this Fermi sea defined above or described above is only defined perturbatively. And if you want to ask what is the non-perturbative reflection amplitude of the hole, you have to give a non-perturbative definition of the hole and the Fermi sea itself.
Yeah. Does this picture that you've drawn tell us that in this situation there is no invariant distinction between a one particle state and a three particle state or a two particle state?
No, that is not. No, that is not. That is not quite a claim. Now, in fact, but this is it's a bit of a subtle issue. So in fact, a priori, it's not so obvious that the S metrics for these things are well defined, because asymptotically they behave like massless particles in 1+1D, and there are all kinds of subtleties about scattering of massless particles in 1+1D, because the wave packets are all propagating the speed of light and they don't separate. So it's not obvious to define asymptotic states. And there's some subtlety with regard to you have several close-string kind of product. Which one you kind of create first?
Actually, this is precisely the reason I was thinking that normally you distinguish one particles from two because two particles separate away from each other. It's very clearly not one particle. But here, they're not moving away from each other, so how do you really tell?
Yes, that's a fair question. And I don't actually have a deep answer for this. It just happens that for this system that somehow there is a well-defined S matrix, and I think it has to do with it has to do with some specific property of the interaction of the system. It's like maybe as not exactly the same, but you can. I think one analogy is the situation with infrared divergence in higher dimensions, where depending on exactly what the interaction is, the S matrix may or may not be well defined. I don't have a deep explanation of why that matrix is well defined, other than that if you compute it following this LZ prescription of more plus a regulum, there is a well defined answer, and that actually matches with the worldsheet prescription.
Yeah. Can I make a comment here?
Yeah.
So if you start with the ripple, then it depends on how far above the Fermi surface various parts of the ripple are. So because they don't move at the same speed, so so soon enough, because of the nonlinear dispersion of the original Fermion theory, the ripples get split. I mean, the various parts of the ripple move at various different speeds, and then
Well, but asymptotically they all move at the same speed, right? Asymptotically they all move at the speed of light.
Well, you can actually see that the particle creation in the bosonic language does happen because of this nonlinear dispersion relation. I mean, if you have
I mean, of course, but I mean that's that's another equivalent with the computed amplitudes. But I'm just saying that a priori, if you look at the structure of asymptotic states, if you don't know the details of the interaction, then you might worry that there's no well-defined S matrix, which is the case for many 1+1D massless systems, for the basic reason that the usual physical definition of S matrix does not apply because the wave packets do not asymptotically separate automatically. So that's all I'm saying. But it just happens in the system somehow there is actually some way to define S matrix that actually gives you a finite answer.
Can I make a comment here?
Yeah.
So it may be something to do with the fact that asymptotically the coupling goes to zero, right?
From the string theory, okay.
So maybe even if you don't
that
separate,
is true. That is true. Sure, but I mean, I guess that falls into this category of things I was referring to, which is just that. Yeah, I guess you're saying that that's basically the reason why this S matrix is actually well defined. It would not be expected to be the case for generic 1 + 1D, say a quantum field theory.
that's right. Yeah.
Yeah. Okay. I think that's right.
Sorry, but could I just ask again? Even if the interactions are switched off, even in the sort of more or less non-interacting theory, if I just look at a state, how can I tell what part of it is one particle and what part of it is two particles? I was thinking at more trivial level, even ignoring interactions, just at the level of states, how do you distinguish between just at kinematics, where you call something one particle and two particles? From the point of view of the fermions, it didn't look so obvious to me that there was a clear distinction from your diagram. But
yes, I think maybe my diagram kind of was meant to clarify some issue, but it ended up becoming more confusing. There was meant to explain why, even though the fermion just scatter into a single fermion, the particle can be created. If you want to, it's not exactly true that you can interpret this particle pair as several particle whole pairs, because you have to create them in order. If you switch the order of the creation around, then it would not work.
okay, thanks.
Yeah. I'm not sure if I can give a, well, okay, anyway, let me just leave it at that. Anyway, the point of this discussion is to illustrate the structure of these amplitudes. So I'm just going to work in the example of the 1 to k scattering amplitude of such a system. As this kind of picture kind of suggests, there's a more cluster and Raghulam gave an exact formula for this, and the formula looks like this. So you take the energy omega goes to, so these atomized states are just labeled by the energy omega 1 through omega k. Of course, energy is conserved. So you take the set omega 1 through omega k and you split into two sets. Let's call it S1 and S2. There's some sign which is not so important, and then the total energy of the S2, if you integrate x from 0 to the energy, you take the particle reflection amplitude where, let's say, we're going to get the picture. So there's mu, which parameterizes the Fermi energy away from the top of the potential. So the particle will have energy minus mu plus omega minus x, and the whole has energy minus mu minus x. So the x is sort of the parameter that goes from 0 to the set, well, to omega of S2, that basically, in this diagram here, it corresponds to the energy of the whole that's being scattered, and this omega minus x is the energy of the particle. So basically, the total energy is distributed between the whole and the particle that's being reflected. That's roughly what it says. Now, the particle reflection amplitude, this is just you can solve the Schrodinger equation with the appropriate scattering wave function for the fermion. It has a known answer. It looks like this. Up to some factor, which is convention dependent of how you define your asymptotic state, it looks like this. 1 over 1 plus e to the 2 pi e gamma 1/2 minus IE gamma of 1/2 plus IE, where E is this argument here. It's supposed to be the actual energy of the fermion. The convention is that the top of the potential is the energy 0. Okay, so you're supposed to think of, by the way, I should say that mu is going to be related to 1 over the string coupling of the string theory. So here, of course, I'm working in the units h bar equal to 1. So 1 over mu is plays the role of h bar. You're supposed to think of in the perturbative regime, mu is large, whereas energy is something of order 1. This E is minus mu plus something of order 1. So e to the 2 pi e is exponentially small. So this factor represents, going to give rise to some non-perturbative effects, whereas this part is perturbative. More precisely, because this E goes like 1 over string coupling, if you take this and expand, take this perturbative part, and this perturbative part, if you take this and expand in string coupling, you'll find an asymptotic series. By the way, this is in the integrand that we had to integrate, but this is not so important for what I'm about to say. So if you take this ratio gamma function and expand, you get an asymptotic series. But it's actually known that this gamma function of 1 over the coupling is kind of the prototype of the perturbative series that's asymptotic, but Borel summable. And the result of Borel resummation gives you back this gamma function. So more generally, one can show, based on some old mathematical theorem, based on very general properties of these functions, that there's actually integrated quantity, that if you ignore this non-perturbative part, if you only have this gamma function, then one can show that this amplitude, as a function of the string coupling, which is going to be identified with 1 over mu, if you just expand it perturbatively, you have asymptotic series, but it Borel resums to the perturbative part of what I call the perturbative part of the amplitude, which is the reason for the name. And the non-perturbative part represents corrections on top of that. Okay, so later I'm going to identify the perturbative part of this with the perturbative string amplitude and the non-perturbative part as the actual D-instantons corrections. So these are non-perturbative corrections on top of the Borel resummation of the perturbative series. That's what I mean by the non-perturbative effect. Okay, so and finally, let me explain our proposal for what the non-perturbative definition of the sequence matrix model actually is, because so far I haven't explained exactly, what is the non-perturbative version of the Fermi C and what is the whole. So the idea is that we want to think of instead of just filling the right side of the Fermi C, which is only makes them perturbatively, we want to replace this statement by filling all the scattering states of the fermion that correspond to, some fermion coming from the right, they can tunnel to the left with some exponentially suppressed, tunneling rates and get reflected back. We want to fill all such energy levels, in contrast to this other kind of scattering state where you have fermion coming from the left and tunnel to the right. So if at energy E, let me call this E right, I'll call this fermion state E left. So these are E right and E left are energy eigenstates, scattering states of a single fermion. So I want to declare that it will fill all of E right, which are the analog of this for E up to the Fermi level, which is minus mu, but do not fill any of the E left states. Okay, so I think this is the appropriate analog, which is a natural non-perturbative general extension of this picture over here. And one of the consequences of this, so the proposal is that this is supposed to be the state in the matrix model that's due to the closed string vacuum. And we're still working with the same matrix model, the exact same Hamiltonian, but we're going to change what we mean by the quote-unquote closed string vacuum state. And then we'll have to talk about excitations on top of this. And one can try to, of course, the particle, the fermion is what it is. And the whole, you have to be a little careful. You can try to define it more carefully by some LAZ prescription. But the upshot is that the key to this non-perturbative proposal is that the reflection amplitude of the whole will end up being the inverse of the reflection amplitude of the particle. So this will be the key relation. Let me explain this a little bit. So,
question.
Yeah.
So does this mean that in your vacuum there is a uniform flux of particle number to one side?
Yes, there is, and it breaks time reversal symmetry and things like that.
And is this this flux? What is the interpretation of this flux in the on the space-time side?
There's no direct explicit interpretation as far as I can tell, because the proposal is that this is the thing that's supposed to be used as a closed-ring vacuum. Now, we can speak of excitations on top of this, and that's what they are doing too. But this thing, the proposal is that, I mean, because you're not supposed to match the fermion to anything in the string. Well, yeah, I mean, you know, the proposal is that this is the vacuum, and you have to match things that are excitation on top of the vacuum.
So now you have two different vacua, right? You could switch left and right.
Yes.
So what is the interpretation of the two different vacua on the bulk side?
But if you switch and left and right, you are changing everything, right? I mean, it's a totally different background of the Stiglitz string theory. I have no idea what it is. Well, I mean, of course, it's supposed to be isomorphic to the Stiglitz string theory, but you know, it's similar to saying that okay, I can also fill both sides of the Fermi sea, but you know, but from the string theory point of view, it's a totally different string theory. So I can only, so far I'm only going to describe for the moment, you know, let's say perturbative excitations, which are, you know, the closed strings. Then we can talk about what happens if you move a lot of fermions, you know, from one side to the other.
Okay, thanks.
Yeah. Okay. So but let me discuss briefly this consequence of this the idea that the reflection amplitude of the whole is the inverse of the reflection amplitude of the particle, which actually looks a little bit strange for the following reason. You know, if the reflection were unitary, if there were no tunneling, then the RP would have been a phase, and the RP inverse would be the convex conjugate. That would actually be the case. Okay, let me come to this in a second. So here, of course, there is actually this tunneling, and you can see explicitly here in this formula that due to this non-perturbative part, the absolute value of the reflection amplitude is slightly less than 1 because of tunneling. So that means that the absolute value of the reflection amplitude of the whole is slightly bigger than 1. So how does that make sense? Well, heuristically, it kind of makes sense because you know, there's if you have a hole on the right side, I mean the left side is kind of already filled with holes. So even if you have no hole coming from the right side, the hole can kind of a fermion that tunnels to the left corresponds to a hole that tunnels from the left to the right. And so heuristically, it kind of makes sense that the reflection amplitude of the hole can have a modulus that's bigger than 1. Now, to make this more precise, one has to carefully analyze this from the LZ kind of language. But as heuristically, this is kind of consistent with the picture. This is in contrast to the type 0b matrix quantum mechanics, which just amounts to filling the both sides of the Fermi sea. And in this case, one can show, which was shown in more Flessen regulum, is actually fairly easy to see that in this case, the reflection amplitude of the whole is RP star rather than RP inverse, in which case this modulus is slightly less than 1. This is going to have a consequence if you plug into the formula, here. So in particular, this non-perturbative, you know, collective mode scattering amplitude I'm going to be talking about in this version of the matrix model, which is what I refer to as the non-perturbative C=1 matrix quantum mechanics, will be explicitly different from in this case, which is the 0b matrix quantum mechanics. The answers are explicitly different, and we can compute this completely explicitly. And in fact, let me just say a few words about the structure of this expansion, which is already very. Yeah.
Sorry, could I ask? When you say your vacuum, you said was filling all of the ER states. Now, a particle is adding one more ER state on top of that, one higher energy ER state on top of that. Is that what a state?
Roughly speaking, yes. So by the part, I mean, yeah, essentially yes. so here, with a particle, of course, I'm thinking of asymptotic states and have to define this. I have to define this in terms of in and out states rather than ER by itself. So
right, but you send an asymptotic state from the right, and then a little bit of it goes to the left, and that's that part of the ER state.
Yeah, that's right. That's right. And of course, I don't keep track of what goes to the left. I will always measure, the asymptotic states by looking at how it behaves in the far right region.
Okay, and what does a hole mean, please? Is a hole a removal of one of these ER states?
Yes. So as I was saying, to define this more carefully, one has to use this LSZ kind of prescription and look at the fermion creation annihilation operator pair and take some LSZ limits. But yes, essentially it means to remove a fermion. But in order to discuss whether in and out hole states, one has to be careful.
Thank you.
Yeah. Okay. So let me describe the structure of the expansion. If you take this, if you just take this prescription and plug into amplitude, plug into this formula of more plus or regulum. So you can expand in the string coupling, which goes like 1 over mu up to some factor of 2 pi. It looks like this. So you'll find that there's a perturbative expansion, which is takes the form of genus expansion, 1 over mu to some k minus 1 plus 2g. G is like the genus. There's a perturbative part, genus G, 1 to k amplitude. And if you, this series is going to be asymptotic series, but I'm going to define the sum as the Borel resummed answer. It will turn out to be Borel resummable, and you can write this Borel resummed answer. And then on top of this, you'll find a instanton expansion. This instanton expansion just comes from this factor here. If you plug in and expand in the integrand and then to the integral, turn order by order, it's easy to produce this expansion. So this is e to the minus n over g string. N is the instant number from 1 to infinity. Sum over L from 0 to infinity. 1 over mu to the Lth power, n instanton at L loop order 1 to k. Now notice that while this is also Borel resummed. Okay. Now notice that while this 1 over mu expansion here involves power to 1 over mu to the 2g. Here this involves 1 over mu to the power L, which is the open string perturbative expansion as opposed to the closed string perturbative expansion. So somehow magically you already see the distinction between. You already see that somehow open string should play a role just by looking at the powers of mu that show up. And this will, the claim that this is going to be to match with the worldsheet D-instant computation will provide some checks of this proposal. But before that, let me just mention that what has been actually checked at the perturbative level. So the history of the subject was kind of weird. In the early 90s, when this proposal was first made, of course, the matrix model was very quickly solved, but the worldsheet side is a bit tough because it involves Liouville theory. And when most of the paper on the subject in the early 90s were written, that was before Dorn, Otto, and Zablochkov found the exact solution of Liouville CFT. And I should say that this sequence 25 Liouville theory is really a strongly coupled conformal field theory. So usually one writes down some Liouville Lagrangian, but it's really only a semi-classical description. So without knowing the exact solution of Liouville theory, how would one go and compute scattering amplitude? Well, so the answer is that basically people try to compute by cheating, and sometimes these cheats work, sometimes didn't work. From the modern perspective, we can understand why the cheat sometimes work, why it didn't work, by looking at the actual Liouville coordinate function decomposed into conformal blocks and how you deform the contour and all that. We can understand how it works. But if you just directly calculate this worldsheet amplitude by integrating correlation in Liouville theory, it's a very non-trivial thing to do. And in most cases, we can only do it numerically. But in the cases where we can do it numerically, this has been checked. So, for example, the perturbative amplitude at g0, well, if you can say 1 to 1, this is just identity. But here, whoops, what happened? Here we adopted a slightly unconventional normalization so that we normalize the asymptotic state slightly differently, so that this identity part of the scattering will be the amplitude will be defined as omega because of normalization. The perturbative tree level 1 to 2 amplitude is some polynomial expression in the normalization, where this is omega going to omega 1 and omega 2. This will match with the worldsheet computation of just the 3-point amplitude, which is very easy to compute. Now, you might be surprised by this answer from the worldsheet point of view already, actually, because the 3-point function of vertex operators in Liouville theory is given by this very complicated DOZZ formula. But it turns out that if you impose the Mash-Out condition, so the omega is equal to omega 1 plus omega 2 from the energy conservation in the x0 factor, and if you impose this on the Liouville 3-point function, then this very complicated DOZZ formula actually in this case passes to some very simple monomial, and it reduces to this expression in the case of the 3-point amplitude. And by the way, there's also historically there was this so-called Lexel factor that caused a great deal of confusion. From my perspective, well, in fact, I'll come to the Liouville theory in a moment. But if you define the Liouville vertex operator appropriately, which is through delta function normalized operators in the Liouville CFT with delta function normalized 2-point function, then the Lexel factor is automatically taken into account, and you don't have to worry about it. So if you compute amplitudes using the appropriately defined vertex operators, it will just match head-on to the matrix quantum mechanics answer. If you take as another example, which is slightly more non-trivial, you consider tree level 1 to 3 amplitude, which again takes some kind of polynomial expression in this normalization of asymptotic states, like so. So this is already kind of a non-trivial, because if you compute this from the worldsheet point of view, a priori involves the integrating, Liouville 4-point function and multiplied by the time-like boson and the ghost part. And this Liouville 4-point function is some very complicated object. So the only way I know how to write it is how to compute it is by integrating the conformal block decomposition of the Liouville 4-point function and integrating over all the possible intermediate Liouville momenta. So this expression means that here you have to take the DOZZ structure constants multiplied by the Virasoro conformal block for the series 4 points. So this I don't only know how to do numerically, but the miracle is that once you integrate over the moduli and carefully regularize, you end up with a very simple expression, even though the Liouville 4-point function itself is some horrendously complicated thing. So this was checked numerically to high accuracy. And by the way, in the 90s, people had other tricks to use to calculate this. We understood why those tricks based on the continuation of the momenta kind of sometimes work, but other times it didn't work, and there are good reasons for that. But if you want to compute it honestly, this is the computation you have to do. As another example, if you consider the 1-to-1 amplitude at the 1 loop level, it has some expression like 1 over 4 I omega squared. So this is omega to omega, some polynomial expression like so. Okay, so here it will turn out that a part of this is fixed by unitarity cut, but then there's a part that is not fixed by the unitarity cut relation. That will provide a genuine check of the perturbed duality. So to reproduce this, you have to study the worldsheet 2-point amplitude, which involves integrating some torus 2-point correlator in the moduli. So you integrate this on the torus, and you integrate over the fundamental domain of the Z. And this thing you have to, the hard part is to calculate this thing in trivial theory, which would involve sort of the component block decomposition of P1, P2 of P1, P2, either in this OPE channel or in this alternative channel, which is P prime, where it's P prime. So it's either one or the other. They're supposed to be equal, but the numerical efficiency, depending on where you are in the moduli space, one might be more convenient than the other. So as I mentioned at the very beginning, a few years ago, we developed some efficient technology to compute in some recursive way these genus 1 Virasoro component blocks, and that came handy. So you can put this on the computer and try to calculate. These are pretty tough integrals to do. They are kind of 6-fold integrals of some very complicated functions which you have to approximate and interpolate. At the end of the day, if you do that computation, we reproduce this answer up to 1% error, which convinced us that we're on the right track. And this error mostly comes from doing all this interpolation of these very complicated component block expressions. Okay, so the upshot is that at the perturbative level, it was checked that it worked in a very non-trivial way, and we're going to proceed by assuming that duality is true, at least at the perturbative level, and then talk about the non-perturbative correction. But are there any questions regarding this?
Yeah, may I ask a question about this leg poles thing? So so as you know, there was a paper by Polchinski and Natsume who interpreted the existence of leg poles as saying that the leg poles indicated that there were other degrees of freedom, gravitational and various other higher stringy degrees of freedom. In particular, it meant that there was a graviton exchange. So you take the matrix model answer, you multiply by leg pole, and you interpret that in string theory. And if you look at the leading pole of the leg pole, that corresponded to graviton exchange. So if you don't have a leg pole now, so what happens to that story?
I don't have anything to say that, but it's not part of my story here. So what I'm saying is simply that there is a set of BRT called multi-classes I can write down in the worldsheet theory with the natural normalization for the vertex operators, which are given by the 2-point function, and they match the results and match head on to the matrix quantum mechanics. There was no molecular factor anywhere in this discussion. Now, what was called the molecular factor would appear if you want to interpret these Liouville vertex operators in terms of its wave function, in terms of the Liouville field. But I don't actually even ever go through that step. Maybe I should write down something in order to explain this point. So usually, the Liouville CFT, if one wants to write the Lagrangian, one would write the action for the Liouville theory in the usual way, in terms of Liouville field phi. Now, as usual, this Q is the background charge, B plus 1 over B, and C is 1 plus 6Q squared, and B goes to 1, limit C goes to 25. That's a theory of interest. Now, in this case, for any C of the Liouville theory, essentially, the only Virasoro primaries of Liouville theory are labeled by scalar primaries labeled by the Liouville momentum P. So P is some non-negative real number. So this represents some kind of scattering state. The only way, the theory is strongly coupled, but we can describe its wave functional in the region where phi goes to minus infinity. So that's a well-defined statement. And as is well known, this vertex operator as a wave functional in that region looks like e to the Q plus P phi. plus the combination of the incoming and outgoing plane waves. The shift by Q is for the due to background charge for the usual reason, and then the differ by the scattering phase S of P. Now, but this is how the Liouville vertex operator was written down in the old literature, which would require introducing the Lagrange factor if you want to match this to string theory. This is actually the matrix model. This is kind of unnatural from the CFT point of view, because I just want to define my vertex operator so that the two-point function is delta function normalized. And to do that, I actually want to put these two incoming outgoing wave on equal footing. So I will simply rescale the whole thing by s to the minus half. So it looks like this. And actually, that difference is the Lagrange factor. The Lagrange factor, this S of P, this Liouville reflection phase, is this thing. Oh, maybe I missed a square here. So the S to the 1/2, this is the Lagrange factor. But what I'm claiming is that if I use this definition of the Liouville vertex operator, which is natural from the CFT point of view, let me say it this way: if I have bootstrap Liouville CFT, I know that this is T-25 unitary CFT with so-and-so property. The only primaries are scalar primaries, and the OP coefficients are DOD coefficients. I don't ever go through the step of the Liouville Lagrangian, and I declare that I'm going to use this to define what I call a sequence string theory. Then I will never have to worry about the Lagrange factor in any of the steps. And that's the situation here. So it's perhaps true that there's some nice, interpretation of this from the space-time point of view, but I think that has to do with how you relate this to the semi-classical description of the Liouville field phi. If I only think about asymptotic states in terms of the VP and don't think about this dependence on phi, then I don't have to worry about this Lagrange factor.
Nice.
Yeah, so I don't have anything useful to say about the story that you mentioned, but for me, the story is simply that I'm going to define a vertex operator using this VP, normalized in this way, and there'll be no Lagrange factor.
But just to continue with that, were to think of this as an S matrix from the point of view of space-time, you would normally try to create a particle that was simple going in, and then did whatever it did coming out. So from the point of view of space-time, the second normalization does seem like the more naturally interpreted one in terms of S matrices. Do you agree with that?
Yes, what you're saying is true, but I mean, usually this is phrased as saying that, one often say this as indicating that the map between this Liouville field phi and the classic, the asymptotic coordinate of the classic model, the matrix model, is non-local. I mean, I think there's no question that the Lagrange factor has a consequence if you want to interpret the wave function of the asymptotic states in terms of the dependence on phi.
So it has physical meaning from the point of view of space-time. Okay, great. Yeah.
That's true. That's true. That's true. Yeah, but we know what it is, and it's simply captured by this normalization of the phase.
Okay. Yes. Thank you.
Yeah. Thanks. Okay. So all right. Let's see. Let me just say that the vertex operator of the closed string incoming outgoing states, in and out states, are just as usual. There's something e to the plus minus I omega x naught, and the Liouville VP, where P is omega over 2 in my convention. Okay. Anyway. Okay. So now let me actually come to discussing the incident correction to this. So let's see. So earlier I said that there's this expansion of the swarm, and you can go to plug this into this formula and easily produce the infinite expansion. So let me just write down a few examples of what they look like. So for example, if you take the 1 to k scattering amplitude and look at the 1 instanton contribution at the 0th order in open string, in open string expansion, it looks like something like this. So some factor sinh pi omega product I from 1 to k sinh of pi omega I. So okay, so now there's some sinh function involved as opposed to some polynomial expression. And if you go to the next order, for example, in the 1 instanton term, the next order in open string expansion, 1 to 1, this you know, is some explicit, slightly more non-trivial function that looks like this. There's some tanh and there's some sinh. Okay, so anyway, they're quite explicit. And the claim is that these are going to be reproduced up to some small subtleties, which I'll explain, by the worldsheet computation based on the D-instanton. So what is the worldsheet computation? Well, you might expect that the leading order diagram for this 1 to k amplitude will look like this. You want the order characteristic to be as big as possible. So that will involve k plus 1 disconnect this. So the k plus 1 of these. And for example, for the, let me just restrict, in the case of 1 to 1, it's just a pair of disks with the you know, V plus and V minus. The next order in open string expansion will correspond to some diagram that looks like this. As I mentioned before, there's also going to be a diagram like this of the same order in perturbation theory in the D-instanton expansion, like so. In fact, you might also imagine a diagram like this, where you have 2 discrete disks, but a disk with 2 holes. This will be formally the same order. Now there are all kinds of you know, several divergences in these diagrams that one has to deal with, but we'll follow our notes in treating these shortly. Okay. Are there any questions about the structure of this of the worldsheet diagrams? Now, of course, I haven't actually said what are the boundary conditions. So the thing I really need to explain is, you know, what are the D-instantons in C equals 1 string theory. Well, following our notes, usually the D-instantons are, at least the simplest type of D-instantons, are supposed to be localized in space and time. And so because we have x0 and the C equals 25 trivial theory, you would say that the simplest kind of D-instantons are boundary conditions, defined by boundary conditions on the worldsheet that are Dirichlet in x0 and some kind of brane in trivial theory. And the only kind of brane in trivial theory that's supposed to be localized in the trivial target space is the so-called ZZ brane. So let me draw a picture. Here's the trivial target space, this new potential. Earlier I mentioned that there are these FZT branes, which are semi-infinite. But these things will have essentially infinite action, and they will, you know, they're kind of infinite massive objects as branes, and as D-instantons, they will have infinite action, and they will not contribute. Furthermore, you know, they kind of mess up the asymptotic boundary condition also, so they will not contribute. The ones that's relevant are the ZZ branes, which are sort of be localized in the strong coupling region heuristically. So the basic type of D-instantons are going to be defined by the Dirichlet boundary condition in x0 tensor with the ZZ boundary condition in the trivial theory. And generally there will be, you know, there'll be one instanton, and then there'll be multi-instantons. So you can have, you know, time x0, and you can have D-instantons kind of localized at different times, say x1, x2, x3. So this is a convolution of 3 instantons. This these are collective coordinates, and you have to integrate over all these collective coordinates. Now, you could ask whether these are all there is. Now, unless, if you're doing something like type 2B superstring theory, there will be D-instantons and anti-D-instantons, and which will also be the case in actually type 0B string theory. But in single-one string theory, it appears that there are no, there aren't distinct anti-instantons, but there are actually other ZZ boundary conditions, or there are other types of ZZ branes. In fact, if you look at the original paper in '99 by Zamolodchikov and Zamolodchikov, in which they discovered this ZZ boundary condition, they actually described not just one, but a 2-integer parameter family of ZZ branes. So, so there are a 2-integer parameter family of ZZ branes in the general alluvial theory, where n greater than or equal to 1. Let me describe the defining properties of these boundary conditions, because I mentioned this because they will play a role in what I'm about to discuss. So we can describe in alluvial theory, we can describe this in terms of boundary state. So if you put this on a cylinder, so this is alluvial theory on a cylinder. We'll put the ZZ boundary condition. It defines the boundary state, ZZ, say, of type m comma n. You can, as usual, you can expand this on the basis of each Ishibashi state, labeled by the Ishibashi state associated with the VP, the alluvial vertex operator. Some normalization, some one-point function psi m comma p, m comma n of p, where this psi is the same as the disk one-point function of VP, subject to this this m comma n boundary condition. Okay, so what are these things? So the defining property of this is such that if you look at the alluvial theory on the strip with let's say with 1 comma 1 boundary condition on one side, and with m comma n boundary condition on the other side, the Hilbert space on the strip contains only one Virasoro. I should use black. Contains only a single Virasoro primary on the strip, which has which is a degenerate primary with a degenerate descendant at level m times n. So in the case of C equals 25, actually this thing has weight 1 minus m plus n square over 4 in the C equals 1. In fact, this is slightly subtle. So in the C equals 25 case, it might look like this thing only depends on m plus n, but actually you should think of this as taking a limit of b going to 1, starting from the generic alluvial theory, where there's actually a distinct family of this psi m comma n, and the result for this disk one-point function is indeed a function, natural function of m comma n. It looks like this. There's some numerical coefficient, and looks like sinh of 2 pi m p, sinh 2 pi m p over sinh of 2 pi p. So it depends on mn in some non-trivial way. Now, in single one string theory, these things, it was known, it was understood that except for the m comma 1, except for the case m equals n equals 1, to give rise to unitary boundary condition. Oops, let's see what happened. Oh, wait a minute. I hope my pencil did not run out of battery. One second. Let me see it. Let me make sure that my pencil did not run out of. Wait, it's okay. I don't know why. Should be okay. Okay, sorry. Usually it was thought that only the 1,1 ZZ brane defines unitary boundary condition for the unitary trivial theory, and all the others are some non-unitary boundary condition that we don't really care about. It was that was clear if you want to describe ZZ brane, but in the case of ZZ instanton, it was not really clear a priori what the rule is, whether you want to select only the unitary boundary condition or not. It will turn out that this n,1, at least one subset of these boundary conditions will actually be important. And the reason we know that is because if we don't have these, the answer will not match with the matrix quantum mechanics. And if we take this into account with some appropriate normalization, which we fix once for all for each n, then the answer matches on the nose with the matrix quantum mechanics. So that suggests that these things should in fact play a role and are needed for this story to work out beyond the 1 instanton level. Now I should say that while the action of the 1,1 ZZ instanton can be shown to be exactly equal to 1 over GS, which is identified with 2 pi mu. So this gives rise to the effect of e to the minus 2 pi mu that I was talking about earlier. If you had effect of the m, n ZZ instanton, the claim is that it has action which is m times n over GS. I don't quite have so there's kind of a non-rigorous way to argue why this should be the case. The idea is that, so we can compute these this one-point function of VP. The instant action is like the disk 0-point function, where the VP is replaced by identity operator. But the identity operator is not normalizable in trivial theory, so it's not in the spectrum of the delta function normalized over vertex operators. We can formally get this by and continue VP to imaginary P going to I, and this VP, this continuation formally behaves like its proportional identity operator. So if you try to use this trick, then you can get this the action of the m, n ZZ instanton by taking the formal continuation of let's say this. Let me represent this by a picture. So this is the red represents m, n, and the green represents the 1,1 times the action of the 1,1 ZZ instanton. And that's the answer you're going to find by looking at this expression over here. Okay, so the claim is that if you had m, n ZZ instanton, you will behave as if it is the ZZ instanton with n times the action of the elementary one, and it will contribute at order m times n instanton level. Any questions about this? Okay, so
sorry, I didn't completely understand everything about your m, n instantons, but I got the sense that you were saying that there was no systematic way from the point of view of string theory of knowing which instantons contribute and which do not. And
that's right. So let me say it this way. A priori, you would think that anything goes, right? A priori, you would think that any decent-like boundary condition will contribute to this full string theory path integral, whatever that is. But you don't know the normalization. So at least if you have a single isolated instanton of some type, whether it will be described by some boundary state, and you can compute, disk correlators, for example, but you don't know the normalization when you integrate it over the classic coordinate of the instanton. It could have been that normalization is 0. It could be that these instantons simply don't contribute. In fact, you could have asked from the very beginning, why are there D-instantons effects at all in sequence string theory? Maybe there are no D-instantons effects. That's actually kind of interesting because if that were the case, I think it's worth saying this because it wasn't obvious that why there has to be D-instantons effects, period, right? I mean, you could imagine that maybe I just want to define, because I declare that I'm going to borrow some of my perturbative series, which will give me some well-defined answer for the amplitude. Why are there D-instantons effects at all? Well, you see, if you compare to the formula I wrote earlier for the scattering amplitude in matrix quantum mechanics, it looks like this. To say that no D-instantons effect will be equivalent in the matrix quantum mechanics language to be dropping this factor here. You drop this factor. So if you drop this factor in R of E and plug into this formula and calculate amplitude, that will be the amplitude that's supposed to match the sequence string theory without any D-instantons effect. So is there anything wrong about this? Not obviously from the string theory point of view, but from the matrix model point of view, there's something funny about it. So if you want to say that this matrix model is some system of free non-relativistic fermions, then I claim that you can never drop this factor. You cannot modify the matrix model Hamiltonian in such a way that this factor can disappear. The reason is because for this kind of scattering amplitude in quantum mechanics, it has to have some a specific analytic structure on the complex energy plane. In particular, when you continue this expression to a complex energy plane, it has to be posed on lower half plane, which actually this expression does. But the pose arrives in a very peculiar way. So you see that this gamma function, of course, has pose, but under the square root. So you might think that looks kind of bad because they're branch cuts, which is not the expected analytic property of any reflection amplitude of a potential barrier in quantum mechanics. But actually, those branch cuts are not there because the poles always come in double pose, or they cancel against 0 from this factor of 1 over 1 plus e to the 2 pi e. So there's this pose at this e of order mu that are posed only because of non-perturbative correction, quote unquote correction. So if you drop the non-perturbative part, the pose will turn to branch cut and it actually has the wrong analytic structure and so it cannot come from any kind of non-relativistic fermion system. So I don't know why you would want to demand that your string theory has to be due to a matrix model, but if you insist on that, then there has to be some non-perturbative correction. So that's the first reason why I think the D-instantons corrections are there. And if you take this prescription and try to match with the matrix model, then you'll find that there's a natural set of instantons that would have to contribute. I think here we're kind of helped by a few kind of lucky accidents. One is just that in sequence string theory, the perturbative series, even though it's asymptotic series, is actually Borel summable. So there's a well-defined Borel response perturbative answer, and on top of that, there's a well-defined notion of non-perturbative correction. That's not expected to be the case in more general, say, type 2B superstring theory in 10 dimensions. In that case, while there are unambiguous, say, charged instanton contributions in the one instanton sector, in the uncharged sector like these anti-instanton, it's not clear that they are completely well-defined because it could well be that there's ambiguity in how to return the perturbative series, and that will cancel against some ambiguity in the D-instantons prescription. So in general, the story can be very complicated. I don't know, but in sequence string theory, if we follow our notes, will lead to a prescription that declares that there are certain type of instantons that contribute.
And suppose you try to approach this from the point of view of string field theory. You look at the contribution in every possible instanton sector. Should you find that should that be a systematic way of seeing that you get zeros in the other instanton sectors and fixing the normalization or not?
I don't know how to fix the normalization from the string field theory prescription either. Maybe Ashok has some comments on this. But as far as I understand, you cannot fix normalization even with the string field theory.
Yeah, not at present, because and the reason is that you cannot think of D-instanton as a solution in the perturbative string field theory, right? It's like you have different string field theories for every D-instanton sector.
Right.
So you have to fix the overall normalization by hand. Maybe at some point somebody will find a way to get around this, but at present we don't know.
Right. So if you could think of the D-instanton as a solution of the original thing, then that would fix the normalization.
That's right. Yes. Exactly.
Okay.
Yes, but you kind of know that you cannot think of this as, at least not as a regular solution, because if that were the case, it should have action that goes like 1 over GS squared was 1 over GS.
Yeah, but this is like the old story of trying to find 2D branes in the 1D brane open string field theory, right? There was a lot of discussion about this.
Okay. But what is the
Ashok will know.
I was saying that you can start with a background where you have the closed strings with lots of D-branes, maybe filling it, and then try to get everything else from as classical solutions of that. Right? But it's a very complicated process. You have to start with the open string field theory with lots of D-branes, which also includes a vacuum sector, and then you can try to make sense of this
Through some roughly tachyon condensation. What in higher dimensions would have been like tachyon condensation process.
Exactly. Yeah. But I don't know how to do it in this case.
Yeah.
Yeah. I mean, as I mentioned earlier, I think we also don't know how to do that from first principle in type 2B string theory in 10 dimensions. But we can indirectly fix the answer of normalization of the integration D-instanton measure by comparing to the answer predicted by S-duality. So in some sense, if you assume the theory has S-duality, then there's a fixed D-instanton prescription. But if you didn't know that to begin with, I don't know how you would fix normalization.
I think in principle, you could think of type 2B as being defined on the classical vacuum, the usual vacuum plus lots of D9 bar filling it. You take that as your defining theory, and then I think everything else can be thought of as a classical solution in that theory. But it's I don't know how to make it practical. It's in principle.
I see. That's interesting. Okay. Okay. Okay, that's an interesting suggestion. All right. Anyway, so Shiraz, anyway, my answer to your question was just that a priori anything goes, but we need to fix normalization, and in this case, there seems to be a simple prescription that we get by comparing with the matrix.
Thank you.
Model. Yeah. Let's see where. Okay. So let me actually come to the details of this computation, which is fairly simple at leading order. So at leading order, let's say for the 1-to-1 amplitude at the 1 instanton level to the 0th order. So this will be at order e to the minus 1 over gs with the gs to the 0 power. So the diagram that contributes is simply this. Where we have the omega plus, the omega prime minus representing the incoming and outgoing closed string, and the boundary conditions are the same instanton at location x0. So in practice, the actual expression for this is that so we have e to the minus instant action, which is this e to the minus 1 over gs. We have the disk 1-point function of the closing vertex operator, like so, with boundary condition ZZ at the x0, and we have the omega minus on the disk with boundary condition ZZ and at x0. And then we have to integrate over the collected coordinate of the instanton dx0, and with the normalization, which is a priori not known, but universal, and we're going to fix this by comparison with the matrix model. These things are just given by the trivial correlator times the this 1-point function x0 part. The x0 part gives rise to e to the I omega x0, e to the minus I omega prime x0 as usual. And when you integrate over x0, you get a delta function, So you have some energy conservation. And then the trivial part gives you some sinh squared because from the form I wrote before with some normalization. So this sinh squared matches what was expected from the matrix model that I mentioned earlier. So here for the 1-to-1, there'll be some sinh squared of the energy. So that's the same sinh squared. And it will also fix normalization n to be some number minus 1/8 pi squared. It's not so important for my discussion right now. Now this seems to be so this is a nice check. It seems to be quite simple because the energy dependence is very simple, just the sinh squared. But this is already very non-trivial because it will turn out that so this matches this matrix quantum mechanics prescription where you take the particle reflection amplitude to be the whole reflection amplitude inverse. It does not match the prescription if you take this to be RP star. Okay, so this corresponds to the type 0b matrix quantum mechanics. So in fact, the claim is that there's a well-defined. So if you consider the 0b matrix quantum mechanics instead, which you fill both at the Fermi C, you don't have to worry about all this kind of weirdness about tunneling, or worry about the time reversal, non-invariance, and things like that. So in that case, if you calculate the analogous amplitude, so the one D-instanton amplitude, you will end up with different answers. So it will not match it with the correction in sequence string theory. Now we actually think that this thing will match with D-instanton effect in the honest type 0b string theory, but that worldsheet theory is totally different, and it will be a separate talk to discuss what happens in that case. This is some work that's still in progress. Okay, and I should say that also does not match some other naive prescription where you put the hard wall there. You also get different answers. So this is what one can check. So the point is that there's a nice agreement that leading order, but it's already very non-trivial, and it's already without knowing what normalization is, it already rules out the possibility that it's due to other types of matrix model completion. But from the working point of view, there's perhaps a much more impressive check at the next order. So at the next order, for the 1-to-1 amplitude at the 1 instant level, but at the next order in open string. So this is the next order in open string expansion. So at order e to the minus 1 over gs times gs to the 1 power. So in this case, as I mentioned earlier, we have the following diagram. So we have the this diagram with the 2 insertions of let's say omega 1, omega 2, or omega and omega prime, I guess I called earlier, and we have the diagram with a disk and an annulus. All of these boundaries are ending on the same D-instanton. So there's the one with these 2 exchanged. 1, omega 2, and finally there is this diagram, omega 1 and omega 2. Okay. Now, as I mentioned earlier, each one. So the first 3 diagrams, they're going to have some open string divergence, but these divergences they cancel against each other because it's because this divergence basically corresponds to the change of open string vertex operator. That's just the collective mode of the instanton. Over here, you have something like this, and over here you have something like this. And when you have energy conservation, so omega 1 is equal to omega 2, all these divergences will cancel. Now, because this divergence is a priori of a logarithmic type, there's a after you cancel the divergence, you have to fix the finite part by cutting off near the boundary of the modular space in a way that's compatible among these diagrams. when we wrote the paper, we didn't know how to do this, so we just assumed there's some universal constant. And then Ashok explained how this can be understood from string field theory. This last case, we also didn't know how to compute this diagram because it requires carefully regularizing things. But we know that whatever it is, if you can make sense of this diagram, it amounts to a order G string correction to the D-instanton action itself. So we're just going to assume that it is some constant times GS. So in other words, this diagram, this set of diagrams, is just equal to some constant times GS times the leading order 2 disk, each one with 1 closed string insertion, which we have already computed. Okay, so now to actually compute the finite part of these diagrams require some work because the non-trivial part, once again, is the Liouville correlator. So you have to compute this 2-point amplitude, a 2-point correlator of the generic vertex operator in Liouville theory, and you have to compute the endless 1 point with the Z-bounding condition. So this is the thing that requires a bit of work because, again, the only way I know how to compute the endless 1-point amplitude, 1-point function of a vertex operator in Liouville theory is to use the conformal block decomposition. So you can either represent this as decomposing a conformal block in this way, in this channel, or you can decompose this in a different channel, which looks like this. There's 3 points, and there's this 1 point. Okay, so there are these 2 different channels, but luckily we have already computed these conformal blocks because we did the same computation almost in studying the perturbative genus 1 2-point amplitude. In that case, we need to use the torus 2-point conformal block, and this endless 1-point conformal block are actually just a restriction of the torus 2-point conformal block to a special value of the moduli, to the holomorphic part of that block to a special value moduli. So this is related to the torus conformal block in this channel, and this is related to the torus conformal block in this other channel. So we don't have to, so we already have these conformal blocks, but still, these are very complicated expressions. You have to compute this by some recursion formula and make some truncation, and then you interpolate this on the moduli space of the 1-punctured annulus, and then you numerically integrate. So you have to integrate over a 2-dimensional moduli space, 2 real dimensional moduli space of the 1-punctured torus, and you have to, on top of that, you have to integrate over the 2 Liouville momenta P1, P2, or P and P prime. So that's still a very non-trivial numerical integral to do, and this leads to some small numerical error, and we think this is the source for the 1%, again, the 1% error that was the difference between the constant that we got by fitting the answer with the matrix model and from what Ashok got from string field theory. So what we did is simply that we fit this unknown constant in this cancellation of through this Fischer-Susskind-Polchinski mechanism among these diagrams. So there's one constant from that. There's another constant from this 2-hole disk. We fit this pair of constants to the answer. So the matrix model answer at this order is a function of energy. I wrote this expression earlier. Let me just rewrite this again. It's some non-trivial function that looks like this. So it's definitely non-trivial that if you can actually master with this, it will be somewhat convincing that you're on the right track. And so we are able to basically kind of numerically evaluate this. Actually, for purely imaginary omega, the reason is because on the worksheet, if the omega were real, there'd be other kind of power divergences you have to carefully regularize. It's easier if you just and continue both the the worksheet computation and matrix model computation to purely imaginary omega and directly compare those functions. And you get some curve like this, and then numerically they fit very well. You can look at the the plot in our paper, it's you know, you can, by eye you will not be able to tell to see any disagreement, and that allows us to fix these two constants, and the constants we got in this in fitting this constant, you know, that we will encounter after this FSP cancellation mechanism agrees with what Ashok had from string field theory up to a 1% error. Okay, so that's the story with one incident contribution. Since it's, I think I've been like talking long enough. I don't know, you know, exactly, you know, how long people's attention span are, but maybe I'll just describe briefly in words what happens to the multi-instant case. So in the multi-instant case, multi-instant case, the upshot is that we're able to match at order e to the minus. So generally we have some expression like this: e to the minus n over gs, gs to the l, or l is some open string loop order, roughly speaking. In the case when a leading order, for any n, we manage to reproduce the answer from the matrix model by assuming that there are m,1 D-instantons. So these things, remember that they have different, this one-point function, the boundary state is different. And the action, the instant action is m times that of the elementary D-instanton that I described so far. But apart from that, the only ambiguity that is there is the overall normalization in the integration measure. So for every m,1 type D-instant, I have to fix normalization by comparing with the matrix model, and it's an unambiguous answer. But once you fix this, everything else matches, which is actually quite striking. And another, so as an example, if you have n equals 2, so you have the 2 instantons. So in this case, there are two kind of contributions. So you have, you can have two separate instantons, the 1,1 type, or you can have a single instanton of the 2,1 type, and they both will contribute. So this one is actually standard, the same as before. But you just change the boundary condition. This first case is kind of a bit more interesting, actually. So the diagram is still this, but actually now you have the situation where you can choose different instantons on the two boundaries of the disk. But on top of that, you also expect to have a non-trivial measure factor, which is of the form. Maybe I'll denote one of these blue. So blue. So you can have diagrams where this is of a different boundary condition. But then, interestingly, you can have a correction to, well, not a correction. You also have to take account of a discontinuous annulus. So there'll be diagrams like e to the this annulus. Okay, so the worldsheet lives in between. Okay, so what is this thing here? This thing is kind of interesting. So if you actually calculate this. This is actually easy to calculate. So let me explain how that works, which is actually very nice. So this guy is just an endless amplitude. So this is equal to integral over the moduli dt over 2t from 0 to infinity of the endless partition function. So now you've got a Liouville theory, you have the x0, and you have the BC system. So the Liouville partition function on the annulus with the z boundary condition on the two sides is just e to the 2 pi t minus 1 over eta of it. From the x0 CFT, you have 1 over eta function from the usual partition function with the Dirichlet boundary condition. And then because the two instantons are separated by a distance in time, let's say the separation is delta x Euclidean, delta x e in Euclidean time, then you have a factor e to the minus t delta x e over 2 pi squared. And then from the BC system, you have some eta function squared, and this eta function factors cancel, and you can just do the integral. Okay, this integral is easy enough to do, and the answer is equal to 1/2 log of delta x e squared over delta x e squared minus 2 pi squared. Okay, so this thing has a nice interpretation. So in fact, this factor is really e to the twice this annulus because you have the strings oriented. So this is just equal to delta x Euclidean squared over delta x Euclidean minus 2 pi squared. And you have to integrate, over these coordinates. So this is the annulus contribution to the instanton measure on the two instanton moduli space. It has a nice interpretation. This numerator is what usually you think of as a van der Waals determinant. This is, you'd expect this because, if you imagine there's some kind of non-abelian modular integration and you gauge fix, you expect the van der Waals factor. Here, string theory is smart. It already knows about this. You don't have to put in this by hand. This comes out from the endless correction. This denominator here is some kind of open string tachyon pole. So this reflects the fact that if you separate the two instantons by distance 2 pi in Euclidean time, actually the tachyonic open string stretch between them becomes unshelled. So this leads to a pole. Our prescription, so you have to come up with some prescription to make sense of this, as often happens when you do the integration over the instant modular space. One possible prescription is to specify a contour that kind of goes around this pole. We find the simplest prescription is simply to declare that we're going to rotate all the contours from Euclidean to Lorentzian signature, and that avoids all these divergences and gives consistent answers, it turns out. So with that, and after some combinatoric magic, eventually we have to, this computation boils down to some combinatoric identities that we cannot prove, but we can check with Mathematica that seems to be true. We can show that the worldsheet computation actually agrees with the matrix model to all instant order for any n, but of course at the leading order in the open string expansion, because the open string expansion is still very complicated going to higher orders. Even in the one case, we can only do that numerically. But at the 0th order in open string expansion, this is what we can do to all order, and kind of matches the matrix model in an extraordinarily non-trivial way, which to us was very convincing that this prescription, even though some aspect of it seems to be a bit ad hoc, like including this m,1 instanton, but it kind of matches on the node, and that was somewhat convincing. So so the conclusion on this story is that we think that the sequence-one string theory defined by the usual worldsheet expansion amended by this instant effect is in fact captures the entire non-perturbatively complete closed string scattering amplitude. It doesn't, if you actually look at these closed string amplitudes, they don't quite saturate unitarity. That's because, that's expected from the matrix model point of view, because there's things on the leaking to the other side. There are, you can kind of bring the fermions, there are fermions coming from the other side, which are not captured by these closed string asymptotic states. There should be some additional states in this non-perturbative completion of sequence-one string theory that make the full scattering amplitude unitary. We're not worrying about that in this discussion, because we're just focused on the exclusive closed string amplitude. So the claim is that for the exclusive closed string scattering amplitudes, they are given exactly by the worldsheet expansion plus the instant contribution. This is, in this case, this is possible to begin with, thanks to the Borel summability of the perturbative series. It's presumably accident of sequence-one string theory. Maybe it has to do with some kind of integrability. It's not expected to be true in more general string theories, especially because in the more general actual, higher dimensional string theories, we expect to also have e to the minus 1 over gs squared non-perturbative effect of quantum gravity, and that's not captured by any of the discussion here. But somehow those effects are absent in sequence-1 string theory, at least within the closed string sector. I strongly suspect that if you go to the non-single sector where you include these long strings and discuss the non-perturbative story there, these gravitational effects might be actually important, and the story will be much more complicated, but we're not there yet. Anyway, so I think I don't have the time to explain the story about the long strings, but I'll be happy to answer questions if anyone is curious about that. So maybe I should stop here. That's gone on for long enough.
Okay, thank you very much, Shi. Let's thank Shi first. Thanks so much for staying up so late and telling us about this. Any questions? Please do keep in mind it's quite late over there.
I'll ask a sort of a quick, vague question, and then you feel free not to answer it, Shi. Which is this: you described how one particular completion, one particular way of giving precise meaning to this inverted harmonic oscillator potential problem matches the string perturbative expansion. Now, as you said right at the beginning, there were many possible ways of giving meaning, completing this hump potential problem from the point of view of fermions, all of which seem sensible from the point of view of fermions. So should we expect that each of these completions has some string theory dual that is yet to be discovered, or was this somehow distinct?
Yeah, maybe, but it's possible that there will be require a completely different worldsheet theory. I mean, I think we just don't. I actually don't understand. Even for perturbative strings. Okay, I guess in this case it's kind of funny because maybe what you're saying is that you expect them to be the same in the perturbative sector. So they only differ in the D-instantons sector.
Yes.
Yeah, I don't have a useful answer to that. So I guess the first thing you might suspect is that, okay, let me put it this way. It seems that based on the discussion of this construction based on ZZ brane, you actually don't really get a choice. Because at the one order, there's only one candidate in the ZZ brane, and it matches with the prescription I gave, and does not match with any of the other prescriptions I discussed. Any other kind of attempt to complete the matrix model. So yeah, so maybe you say that's kind of puzzling from the perspective that you would expect it to be due to some kind of string theory, and we don't seem to be able to discover it in this worldsheet formulation. Okay, the short answer is I don't know. It's an interesting question.
Thank you.
Yeah.
If nobody else has a question, I have one more quick question, if that's okay. But other people should feel free to ask first. But okay, let me just ask my question. You had the story with the non-singlet sectors and the black hole. Now,
yes, I should mention that I didn't actually describe what the connection to a black hole is, but this is basically spelled out in Huang's paper. Maybe I should give let me give a 1-minute summary of what that is. So this is kind of on a more grounded footing. So the story of Huang, which is in this very obscure section in his paper, at least to me was kind of obscure when I first read it, was that you want to take some kind of decoupling limit of a large number of SZ branes. But this decoupling limit is defined in a funny way. So you want to take, so here we got a Livio, we got a bunch of, let's say, FDT branes, many of them. So there are, let's say, NF of them. And this distance is S. So you want to take the limit NF to infinity and S to infinity, and hold something fixed, some quote unquote coupling fixed, such that you know, it's kind of interesting because first of all, it's interesting that such a non-trivial limit exists, because intuitively you say that you know, the brain has all retreated to infinity, so there's no brain left. Okay, but because the numbers are so large, its influence on closing background remains, and so it should correspond to some deformation of closing background. So what deformation is it? There's some hand-wavy argument that suggests that deformation is actually sine-luvial deformation. So basically, you're kind of deforming the luvial theory by the sine-luvial term, whose coefficient. So it's like you have luvial plus this cosine of something. The coefficient is this Tooth coupling. Okay, so in the in the limit, when you send this lambda to infinity, the sine luvial dominates over luvial, and you're sort of going to the actual sine luvial theory. That's the TDO of the cigar. But there's some interesting intricacy about this, which is, well, one of them is that it seems that, you know, if you actually look at this carefully from the CFT point of view, it only works if you are above a certain critical temperature. So it's kind of a very weird decoupling limit. But if you believe this, which is yet to be kind of fleshed out in some more detail, then the claim is that the black hole can be obtained by the strong subcoupling limit of this decoupling limit, a large number of LTD brains. So if you understand what LTD, okay. So in fact, this is kind of encouraging, because even if you don't actually know the deal of LTD brain, which I think we don't know precisely, in this limit, you may not need to know that. You just need to know that there are these long strings that live on this LTD brain, and there's a large number of species of them. There are like NF squared species of this long string, and that might be sufficient. So the slogan would be that this black hole is supposed to be due to some thermal bath or long string.
Right. So I was going to ask you. So the entropy of the black hole comes almost entirely from the modes on these D brains.
On the most on the D brain.
Right. I mean,
yeah, I guess in some sense you can. Yeah, that's kind of true. That's kind of, yeah.
And these modes live at infinity and sort of very far away. They're sort of weird modes, and they make up all of the states.
Oh, yeah, but you know, they don't. These modes are really these long strings. I would say that it's not accurate to say that they live in infinity, because they have enough energy to come deep into the bulk.
Okay.
And the funny thing has to do with this scaling limit. So the thing is that actually in this decoupling limit, NF is actually exponentially large. If I remember correctly, I think, let me see, what is the precise scaling? I think, let me see. Yeah, so the actual subcoupling limit goes like GS times NF times e to the minus 2 pi S R, sometimes some other function of R, which is not so important for my purpose. So there's some relation like this, where R is where 2 pi R is the inverse temperature. So R is the radius of the thermal circle. So actually, this NF is exponentially large for this in the Stokes limit. So that somehow what allows you to kind of compensate for the very high energy of these long strings. So you have to kind of take the limit kind of more carefully, because the long string limit, strictly speaking, is when this S parameter goes to infinity. Here you have to keep it to be large but finite before you take the limit. So it somehow has a very large number of species that somehow compensate for that. I should say that, you know, it's not really obvious that the details will work out. It's something that we're currently trying to analyze in more carefully. But well, indeed, one of the first things one would like to understand is the black hole entropy from the free energy of this long string.
Okay, thank you.
Yeah.
Can I just ask a quick question?
Yeah.
Yeah. So if I understood what you're saying correctly, so the 4,1 instantons, when they contribute, the 2,2 instantons don't contribute. So
That's correct. That's correct.
And then you have ruled out, the possibility of 2,2 instantons contributing.
That's correct. So we actually checked this explicitly. So for example, at the 4 instanton level, we started by assuming that the 4,1 instanton, 2,2 instanton both contribute, come with some different normalization factor. And we saw explicitly that it just ended up being that the 2,2 instanton, the normalization has to be 0 to match with the matrix model answer. I don't have an explanation of why that should be true. We thought about the possibility that it has to do with, the open string spectrum on the 2,2 is slightly different from the 4,1, maybe there's some explanation based on that one can come up with, having to do with somehow thinking of it by analogy with the several points of passing the group, but we were not able to come with anything precise to say. So yeah, it will be interesting to understand, the reason for this.
Okay, thanks.
Yeah.
Okay, if there are no more questions, let's thank Shri again for a very nice talk.
Thank you.
Ji, thank you so much for staying awake at night and giving us this fantastic, really clear talk over 2.5 hours.
Thanks for giving me the time. Actually, once I start talking, I'm no longer sleepy, so that's fine.
Great.
Yeah, thank you. Thank you so much, Sri.
Thanks.